And again, you might think you're asking questions, which is don't follow my example.
Thank you. Okay, last day, last chance, not really. I'll be around for the whole week, so I hope that you come later to talk to me, ask your questions. I'm sure that there are many interesting things that you can also tell about to me, like just, let's say, if you do some research, I'm really curious to hear about that. Okay, so last time we talked about linear bandits, and I'd like to continue from there. So what was the setting? Setting was this, so we're talking about linear bandits. Yeah, just before that, today the goal would be to finish linear bandits, and then we move on to MDPs. So then we'll try to see whether you can apply the same ideas in an MDP setting, and what MDP settings can be covered, and what is left. Okay, and then to make a full circle, maybe we are going to go back and look at the code, like what the code that I was showing at the beginning is doing. I made a URL, and at the end I'm going to write a URL on the board so you can get my code. So you can experiment with it later, modify it. I think it's a lot of. Okay, so linear bandits. So we have this unknown parameter vector that lives in a d-dimensional Euclidean space, and in round T, you receive a set of vectors, the subset of RD. This is your decision set. This is the set of vectors from which you can choose your actions. So once you're done with that, you have to choose a vector, an action from this set. This is the action. After that, you receive the reward. So in this work, we are assuming in the linear bandit framework, we are assuming this linearity assumption about the reward, that the reward is really inner product. So that's the role of theta star and xt. So that's kind of the mean reward. Given your action, that's the mean reward. And so you're not going to see the mean reward. That would make the learning problem too easy. But you're going to see the mean reward in noise. And eta t is the noise. So it's a real value. It's a random variable. It's a noise. And the noise variables, it could be just an IID sequence, but it could be a correlated sequence as well. So many examples, in MDP examples, for example, you will have martingale noise and like all kind of noises which are correlated in time. They're noise because their mean is 0. So we're assuming that there is no bias. So that's the linearity assumption. Okay. So in particular, the expectation of eta t given xt is 0. That explains why we call this a noise variable. And we make stronger assumption than this. So we want to assume something about the tail of the noise, because if you don't make any assumptions about the tail of the noise, then you can have really heavy tail distributions. If you have heavy tail distributions, then your learning is going to be slowed down. For practical applications, in many cases, not in all cases, you might assume that the tail is not heavy. we call those not so heavy tails sub-Gaussian tails. So that's when the tail of the distribution of the noise stays below the tail of the Gaussian distribution. So the Gaussian distribution's tail, you have this bell curve, and the tail tapers off pretty fast as e to the minus x squared divided by 2. So the sub-Gaussian assumption that we're going to make is that eta t is R sub-Gaussian, but we actually make a modification to this because we want to allow correlated noise. So we're going to weaken this assumption. We're going to say that eta t is R sub-Gaussian conditionally on the past. So mathematically, formally, what this means is that if you take the moment generating function of eta t and you're conditioning on previous values of the noise, and all previous choices of the learner, then this stays below e to the lambda squared r squared divided by 2. If you ever try to calculate this for a Gaussian distribution, you will recognize that you would get something like this with r squared. So it's really just about the tail properties. Like you're exponentiating this variable and take its expectation. How does it scale with lambda, right? So if lambda gets squared, then that's like a Gaussian property. So it's maybe not so easy to see like why we put this condition in this form. It's not so important at this stage to understand this. But this is the condition that we use. Okay. So the takeaway is that if the noise has some nice tail properties, the tail stays below the Gaussian tail. You may allow correlated noise as well, as long as you have this condition, then you will be able to estimate the theta vector pretty fast. And you will be able to construct nice confidence intervals. The confidence intervals that you're going to construct, if you have n samples, typically they would have a width of 1 over root n after n observations. And the size, if you are talking about a confidence interval at the level of delta, error probability, so a confidence interval that holds with probability 1 minus delta contains the true mean with 1 minus delta, then the delta would appear under the square root with log 1 over delta. So that's kind of the Gaussian property. And this implies that. So because of this condition, you're going to see confidence intervals. You expect to see confidence intervals of these forms. Log 1 over delta divided by n. N is the number of observations, and delta is the error probability. So that's the width. It's proportional to that. Okay, so that's just the Gaussian property. Okay, so the algorithm. We talked about the algorithm the last time, and we said that we have this general construction, the awful algorithm. The awful algorithm assumes that someone is constructing a confidence set that contains theta star with high probability. So that's kind of like an oracle or an input that awful assumes. So the assumption is that Ct minus 1 is some confidence set. And later on I'm going to show you some confidence set constructions so that this algorithm is not going to stay abstract, but you can make it specific. So someone's constructing this in such a way that the probability that theta star is in C, well, I want to make this really strong. So I'm going to say that So the probability that theta star is in all of these confidence sets up to infinity, okay? So the intersection of all of them is at least 1 minus that. But data will be chosen to be something really small, okay? So this is the input, if you want, to the algorithm. So once you have this confidence set, so these are going to be constructed based on the data, solving least squares problems and whatnot. The algorithm is super simple. Basically, it chooses an optimistic parameter and chooses xt also in an optimistic fashion. So how does it work? If you take any theta x pair, I want to use lowercase x there, that is such that theta is in ct minus 1 and x is in dt, so it's an low decision vector, then you know that the mean reward for these two guys, if theta was the true parameter vector, would be the inner product between theta and x. So you take your confidence set, and you consider all possible such inner products between all possible theta vectors and all possible vectors in your decision set, and you choose the best of them. You can think about this as choosing the best possible word. Okay, that's theta. Theta represents the word for this algorithm. And given the best possible word, you're choosing the best possible action there. X is the action. Or you can think about it as like for each action, you're investigating how high a value you can get. And then you choose the best action. So this way, we are really generalizing UCB. So a specific case of this algorithm is UCB. If you are over a probability simplex, and you use, basically your confidence set would be specific in that case. It would be this product set. That's an easy to imagine case. So once you have this choice, then, well, that's it. Like it's a one-liner. There is no second step. This is the only thing that you do. That's the algorithm. And you repeat. Okay, so what can we say about this algorithm? So let's assume that ct minus 1, so the last time I started to explain how it makes a lot of sense to think about the confidence sets as being ellipsoids. Because if you consider the Gaussian case, then the ellipsoids kind of appear in a natural fashion. And we talked about that the ellipsoid, the shape of the ellipsoid is going to be determined by a matrix, which is basically the sum of the vectors that you chose in the past, the outer product of the vectors that you chose in the past, plus lambda times I. So you introduce some kind of regularization because this matrix might not be invertible and you want to keep things nice and bounded. Okay. So we have this matrix, and that determines the shape of. We expect that the confidence set is going to be tightly included in an ellipsoid with this shape. So what's an ellipsoid? So the ellipsoid is just like all vectors that are close to some central vector, the center of the ellipsoid, in this weighted 2 norm, this matrix weighted 2 norm. And the last time I argued that the expectation of a quantity like this is kind of constant. So that's kind of the radius. So you expect the ellipsoid radius to be constant. But I want to keep this thing general here, so I'm just going to say that the radius is some beta function of data. Okay? Now I'm going to make some assumptions about beta. The assumption that I'm going to make about beta is that it's really, I allow it to grow a little. The reason I have to allow it to grow a little is because I'm making this condition to hold for every time step. So you might need to expand the ellipsoid a little bit. If you just focus on one time step, then this should really be constant. If you're saying that this has to hold uniformly in time, that there is a small price to that, and that's a logarithmic price. So I'm going to assume that later on we will see in the confidence set constructions that this can indeed be achieved, that beta of t minus 1 delta is of the order of log t over delta. So it grows a little bit with time. It's logarithmically growing with time.
Question.
So it's kind of a uniform.
Is the first line an inclusion or an equality? Definition of Ct minus 1.
Are you talking about this?
Yeah.
So right now it's enough to assume that this is included, right?
But in practice,
so if you are in practice, many times you use this, but it could be that you use something smaller.
okay.
But the proof is not going to be able to exploit that if you use something smaller. This proof, okay? So.
Chab,
Right.
I have another question.
Yes.
So I'm just wondering about when you get started, right? The first confidence bound that you draw, is that basically an infinite ellipsoid?
Not really. I mean, there is this lambda I. I think that's going to help you. But when you get started, like I need to make some assumptions.
Right.
I'm going to make an assumption about theta star.
That
So
it
I'm
isn't-
going to assume that theta star has a bounded two norm, is a non-bound.
Okay.
Because otherwise, like, you
Yeah.
would be in trouble.
Right.
Like,
so
you have no idea about where the ellipsoid should be.
Good. Okay.
But if you have such an assumption, then it's okay. Like, you can put the ellipsoid, like, around 0 with that huge ball, right? So it includes all those theta vectors that are possible at the beginning. So, and here are the other two assumptions. So the next assumption is that we know that theta star is bounded by, I think I call it S, right? And S is going to determine initially this beta, right? So S is going to show up there. Otherwise, you wouldn't be able to do this. And this is not needed for this proof, though. It's only needed if you really want to construct this confidence set. And so this, maybe I put in parentheses. And the real assumption is that I'm going to assume that all these vectors that you can ever choose, or if you wish, the condition is on dt, are going to have a norm that is smaller than some quantity L. Okay? So you can't be forced to choose larger and larger vectors. I think it's a reasonable assumption. Okay. So the reason I'm doing this is because the next steps, the proof. The proof is really fun because it's just a few lines. So we want to show that the regret of awful under this condition is reasonable. So of course it's going to depend on beta, but if beta is of this size, then the regret, we want to show that the regret is going to be small. Okay. So, so that's what we are after. So the theorem is that under these conditions with probability 1 minus delta, the regret is going to be of the order, I'm going to suppress constants. After n time steps, the regret is going to be of the order of d times root n log 1 over delta. Maybe that should be n over delta, right? I reserve the right to put a tilde later on if I discover some other logarithmic factors that I forgot. But essentially this is the result that we are after. So how does it work? It's the proof is very short and nice. because I'm going to hide some, yes.
So what is theta hat in CT minus 1? Is it the...
Right, okay, it should depend on T. While I was writing, I was thinking about that. It depends on the data.
And we have
So
to
we
input
assume that it exists. So we just assume that someone construct these confidence sets, and for those confidence sets, this holds, this inclusion holds, with some theta hat. The algorithm doesn't need to know theta hat, but it needs to know C. So that's a stronger knowledge, if you wish. But theta hat is going to be used in the proof, yes.
Understand the optimism here. So optimism is in that argmax operation.
Right.
And how is it? I don't understand how optimism is helping in the.
That's why I want to do the proof. Because in the proof, I hope that we will see how it happens. Okay? So apparently the first step of the proof uses it, and if you try to do the proof differently, and we can try to do that, then we will see what is the term that is coming in, which is maybe harder to control.
One question that without the knowledge of theta hat t minus 1, we will not be able to do that maximization, right? That is, we won't know the CT minus 1 and we cannot do that maximization.
Well, I didn't talk about the computation complexity of
Not the
calculating.
computation. No, we should try to maximize over some set to get that theta tilde t and xt, right?
Yes.
So unless we know theta hat,
You don't need to know that if you know CT minus 1,
okay.
right? You don't really need to know theta hat. You know CT minus 1, so you can try all the vectors in CT minus 1.
So how do
If
we?
you don't care about computation complexity,
Okay. So
right?
how do we construct that CT minus 1? That you'll be telling me, right?
I will be telling about that later.
Okay.
Yeah,
because-
there will be multiple constructions. So if you have finite and bandit, then we already know that you can take products of intervals, and that gives you a box. That's going to be like a rectangle shaped set. And you can include that into an ellipsoid too, right? And the mean, in that case, this would be the mean reward for each of the arms. So, yeah. Okay. So proof. So the proof is really nice because we are not only proving the regret, a bond for the total regret, for the sum of the immediate regrets, but we can almost show a bond for the immediate regret for time step t. So it's somewhat stronger. So, you know, the regret, as we define it, is so I guess I don't know how I defined it. Did I define it? I think it was the sum of theta star xt star minus the sum. So that's the best reward that you could get, best mean reward that you could get, and this is the mean rewards that you're getting, where xt star was the best decision in terms of the mean reward at time step t, which takes into account that the decision set is also changing. So that's dt. Okay? So we want to bound this quantity with high probability. So if we take just RT, which is the t's term, theta star xt star minus theta star xt. Okay? Let's concentrate on this term. We want to bound this term. I pulled out the t's term from both sums. If I can bound this term, I can bound the sum. So the problem is that when the algorithm somehow comes up with some theta tilde, And here we have theta stars, of course, because we are measuring things against the true world, theta star. And what we know is that somehow theta tilde is going to be in Ct minus 1, which is an ellipsoid, and it's not too big. Right? So this beta is small. So somehow we want to exploit that. Somehow we want to bring in theta tilde, maybe theta hat, and whatnot, and want to get rid of theta star. But theta star is also in the ellipsoid, so that's good. Like if we have these two guys, and we compare the distance between them in this ellipsoidal measure, right, in this weighted 2-norm measure, then we will, okay, so that's kind of the plan. So the question is how to do that. And so the first thing that you can do, and that's like after some thinking, you might discover that, well, we have to use at some step the choice that the algorithm makes. It's an optimistic algorithm, right? So it chooses the best word and it chooses the best vector there, right? And so theta star is in Ct minus 1, okay? And xt star is a vector in the decision set. So these are there in this set over which we are maximizing. So the inner product of these two guys is definitely going to be larger than the inner product of these two guys, right? Because of our choice. That's the optimistic choice that the algorithm makes. So let me write this. So because of the optimistic choice, theta tilde t, inner product xt, is larger than or equal to theta star xt star, and then you are subtracting theta star xt. Okay? And so you can see that nice things happen when you do this. Because xt is the same in both expressions. You can put them together, and you see that the difference between theta tilde t and theta star appears. And those are two vectors in Ct minus 1, and Ct minus 1 has a controlled size. It's a confidence set whose size we totally expect to be controlled, well controlled, small. So let's write this. Okay. So when you are here, then you might realize that, well, all you have to do is to use Herder's inequality, right? With weighted norms. So we have this, this norm, right? So if you have a vector and you put a matrix there, positive definite matrix, its weighted 2 norm is x transpose Vx. And Herder's inequality for weighted 2 norms is going to state that if you take two vectors, where do I put that? If you take two vectors, u and v, then the inner product between u and v is going to be upper bounded by the v norm of u times, okay, too many v's, but and the v norm, the v inverse norm of v. So this is the Dua norm of v. So you can like actually work out the math. This is Herder's inequality for weighted matrix norms. Okay. So we're going to use this. So this can be upper bounded as theta tilde t minus theta star. And important thing, I'm going to use v bar t minus 1. And that's because we expect this to be small. So that's the shape. And then I'm forced to put v bar t minus 1 inverse here. Okay? Good. you can add and subtract theta hat. Both of them are within a beta distance from the center of the ellipsoid that contains ct minus 1. So therefore this can be upper bounded by 2 times beta t minus 1 delta. So now as to this term, if you go back to thinking about the Gaussian case, and you would express this term, then you would see that the size of this, so this is like this vt minus 1 inverse, it has t terms in it. It's like dividing by t. And then you have this norm, but it's not a square norm, so it's the square root of the square of the norm, where you would divide by t. So it's kind of like a 1 over root t term. So this is what I'm not going to show, but you have to believe me that this is 1 over root t. So this is order of 1 over root t. Okay, so that's actually quite a bit of work to show that things work out this way. And I'm cheating here a little bit, but I think it's good. Like it's intuitively, it's clear that this is basically like how much this is the size of the confidence width for your choice, actually. So, and I told you that if you have sub-Gaussian distributions, then after so many observations, this is the size of the width of a confidence interval. Okay? So if you have this, you are summing up, you get the result. Okay? That's it. So this is how we used optimism. If we didn't have optimism, we could try to go some other way. So we could subtract and add, and if you do that, you would see that, I'm not going to show, but you will see that you will need to control the norm of xt star measured in this weighted norm. And this might be hard to control. So that terms pop up, and in general, if you're not making optimistic choices, you're not controlling that term. So optimism is going to force you to explore, not to miss the optimal arm. So this is the optimal arm's confidence width, want to decrease it. And optimism is helping you to explore. Without optimism, you're not necessarily exploring. There are other ways of exploring, but optimism is one way of forcing exploration. And it appears, based on these proofs, that it's not a bad way. Because these rates that we are getting here are basically optimal. So you can prove a lower bound that basically shows that the rate of growth of regret as a function of the dimension, d was the dimension of the parameter vector, is correct. So you can't do much better than this algorithm in terms of the dimensionality dependence. Okay? In a general case. In special cases, you could do better. So for example, if you're in simplex, then we know that d should be under the square root. D is the number of arms. In the worst case bound, we saw that we have square root dn, not d outside of the square root. But for arbitrary shape action sets, this is the best that you can do.
Question.
Yes.
So the order 1 by square root t that you said is the order of the norm of xt with respect to the inverse norm, right? Is that always true irrespective of any sequence of actions that you chose? It looks to me that it's...
What do you mean any sequence of actions?
So
like we are choosing the actions in this way.
No, but Vt minus 1, the definition of Vt minus 1 just depends on a sequence of actions arbitrarily, I mean, a particular sequence of actions, right? So
whether we are exploiting that the way, okay, let me...
Is it just a geometric property?
So I was cheating there big time.
Okay.
So, and that makes it hard to answer this question. Because in actuality, you sum first, you're squaring, you use multiple steps. you basically want to see a square here. That's because of an algebra. The square of this is easier to bound, and it's my guess is so. My guess is that it doesn't matter. But
in the limit, what you will be doing, you will be sampling x star. There's a unique x star optimal arm. You'll be basically sampling it infinite. I mean, increasing frequency, right? So essentially, all those XX transpose terms will become x star transpose. Essentially,
right. Could be, yes.
So
right. Yeah. Then, in that case, it's obvious, right? Yeah. Is my mic off? Okay. Okay, so I promised that I'm going to show some confidence sets. So let me finish with that. So, almost there. And this is something that you can code up and you can experiment with. This is the confidence set for which I've shown the experimental results the other day. So to specify the confidence set, I just rely on this formula. So I'm going to call this A t minus 1. So we're going to use Ct minus 1 equals A t minus 1 with a specific choice of theta hat. And that choice was on the board yesterday. It's basically the least squares estimate. Okay, so that's the center of the ellipsoid, and what remains is to specify what is the radius of the ellipsoid, and for that I have a horrible expression that I have to look up. It's okay. So you have the subgaussianity constant, which basically plays the role of a variance or standard deviation. And under the square root, you have 2 times the logarithm of, oh, this was, I think this must have been squared. Right, so I guess maybe I take away the square from here. Is that good? Maybe put a square there, put a square there. Yes, sorry. Yep, that doesn't change much. Yes, this is going to be under the square root. Yes, that's correct. So the log of the determinant of v bar t minus 1 divided by the determinant of lambda I under the square root and divided by delta. So that's kind of the main term. And here comes the other term that contains s. So this makes sure that initially they're including theta star, because otherwise you have no chance if you don't know s. S was the bond on theta star, it's gone. But so we assume that the norm of theta star is smaller than s. So that's kind of some regulatory assumption that you need. Okay, so if you wish, if you know that you can get an upper bound on this xt, and there you're going to enlarge your confidence set slightly, but it's easier to see what goes on. So by the way, if you're worried about that this computation is too expensive, you can do it incrementally. So this determinant can be updated in an incremental fashion, and it's not that heavy. So if xt is smaller than or equal to L, then you can also use t minus 1 delta equal r times, and here you're going to see that the dimension is going to pop out. It's coming from this determinant. the dimension. Log 1 plus t s squared divided by lambda over that. And the other part is the same, square root lambda times s. So these are confidence sets that satisfy this property. So they are good for our purposes. So interesting thing about this confidence set is that, well, this is what we derived with my former student Yasin Abbas Yadkari, that you can do the same derivation in Hilbert spaces as well. And some people are, like separable Hilbert spaces. So some people are obsessed about, Gaussian processes and reproducing canal Hilbert spaces. They want to kernelize everything. You can kernelize this algorithm. And then you will learning in a large space. Then this condition becomes a smoothness assumption, essentially. Okay. So it's pretty neat. I really like it. So one thing that I just wanted to mention on the side, just to give you something to think about, is that, well, going back to finite dimensions, so many times the way this works is that you're making, this is a feature space, this RD is a feature space. You're making up your features. You're throwing in new features. So you want to, solve this display advertisement problem. You have finitely many arms, and then you want to, you have the customers coming to you, specify the context. So you're going to extract a lot of features about the customers, as many as you can just imagine. So the dimension of D could be really large. So you want large dimensional spaces. You don't want to restrict the user by saying that, oh, you shouldn't extract too many features because then my algorithm slows down. But if you look here, what is the result? It's gone. It was linearly dependent on the dimension, which is like a little bit unlucky. So in machine learning, supervised learning, you might be aware that people say that, well, maybe it's not a big deal to have many features as long as you're not going to use many of them in your predictions. If the true parameter vector would be sparse, so theta star would have many zeros in it and just a few non-zeros, and that's called the sparsity of theta star, then you should be fine. So the question is, in linear bandits, can you exploit sparsity? So we've been working on this, and then there is an interesting line of work, and the answer is kind of mixed. So we are still exploring it. So we can prove a general result that works without any further restrictions on distributions or anything. It's just in this setting, where we are replacing in the regret bound this linear factor. So the regret, remember, it was O of D square root n up to logarithmic terms. So instead of this, with sparsity, we can get, instead of the D, we are going to get square root dp n. So here, the p is the sparsity. So the sparsity, it's also called the zero norm of theta star, measures how many non-zero elements we have in theta star. Okay, so you can get rid of a root d, but you couldn't completely eliminate the dimension. And the bad news is that no one will ever be able to do that. So there are some lower bounds that show that you can't get rid of the dimension in this bandit problem. So it's very unlike the supervised learning setting. Somehow sparsity helps a little, but it doesn't help you all the way. Now this holds if you keep full generalities. So the distributions are not restricted. If you start to make additional assumptions, then it is possible that sparsity helps more. And there is one work by Remy Munoz and Alexandra that shows that that if you make some additional assumptions, then you can actually get rid of the dimension. So the assumption in that work is that somehow the noise is added to the parameter vector in every round. It's not like sitting on the top. Like if you choose smaller vectors, then you reduce the noise. So that's not the property here. If you choose a smaller vector within your decision set, the noise kind of can be the same. So in their setting, you can somehow control the size of the noise. So the signal to noise ratio is better. So whether that is a practical assumption or not, that's a different question. Okay. So that's linear bandwidth. So how does this lead us to, yes?
So lambda here is what you're calling the regularization parameter,
Right.
correct? So does this mean your confidence bounds will never shrink to 0?
They do. They do. So what's strange is that, like, you can think about this as a constant, so it's slowly increasing, but this increases linearly with t. So it's like if you divide by this t, then the whole.
Oh, this is just the. No. So the last line there has.
Right. So you have this lambda times s, but
Right.
this is kind of like the unnormalized radius. So it's like this should be divided by square root t, and then you get the
I
actual
see.
radius.
Okay, got it.
So I write it the other way around, right? So this is t here.
All right, sure.
When you move t there, then it shrinks.
Okay.
So v bar t is growing. That's why it's this way. Okay. Is this good? Okay. So how does this lead us to MDPs? Well, optimism. Just have to keep it optimistic. So if you're in an MDP setting, the same idea works, by and large. So how do we, what do I mean by this? So let me just clean a few things here. Okay, so I'm gonna change just this thing just very, very slightly, and I'm going to claim that this is an algorithm for MDPs, okay? So what do I change? But in an MDP, what is an action? Like, do we really want to choose actions? Sometimes it's better to think about choosing policies. Your policy is your action. Like, you're thinking about, oh, I want to choose this policy, and then you follow the policy, right? So policy sometimes plays the role of an action. So I'm going to redefine the meaning of XT. I'm going to actually say that I should choose a policy. And so I have the set of stationary policies. So the set of stationary policies is, you have an MDP, then these policies are just mappings from the state space to the action space. So S is going to be the state space, and A is the action space. I'm going to talk at first about finite MDPs. So what do we have in a finite MDP? You have S, you have A, the state space, the action space, they are finite. You have a transition matrix for each action, or altogether you have a transition properties for each state action pair, and you have rewards. That's an MDP. Okay. I'm going to assume that, well, there is this agent interacting with the MDP, it doesn't know about P, it doesn't know about R. How should it learn to collect as much reward as it is possible to minimize regret? So, and the claim is going to be that we should use optimism. What is theta? What do you think theta is? Kind of abstractly. What should be the role of theta in the MDP setting? Values simpler. We already said that XT is, or the action is going to be the policies. So policies are out of question. Values are out of question. Going over.
State action pairs.
Sorry?
Which state action pairs?
So when I talked about theta, in the linear bandit setting, what was the expression I used? I said that, like, want to be optimistic, we are imagining the best possible word. The best possible word. So what's the word in an MDP? What are the possible words? I think state space and action space. What are the possible words? How do we describe the word? Right, so we're going to use the transition probability and the reward together. That's going to be our theta. That's what we don't know. That's the unknown. We want to estimate that. So theta is defined to be the pair P and R. That's what we are learning about. That's the word. If we knew what it was, there is a theta star. That's the true P and R. If we knew that, we knew how to act. We would know how to act. Okay. So in order to finish the specification of the algorithm, all is left is to specify CT minus 1. Right? So what are the confidence, what is the confidence set for all possible words? Well, you can imagine this thing that, you visit certain states multiple times, and for a given state, an action, when you're using that action multiple times, you will see next states multiple times. You can construct an empirical estimate for the next state distribution. Okay? So at any given time, you can construct this model. This is what we started when we talked about that reverse swim MDP, that we are estimating the transition probabilities, and we are the same way you can estimate the rewards. Okay, so at any given time, P hat and R hat could be empirical estimates of P and R. So that's similar to theta hat. It's like the least squares estimate. It's apparently you could write it as the least squares estimate if you wanted. So then what's CT minus 1? So if you have these empirical estimates, then CT minus 1 should collect all P and R such that somehow the transition probabilities in this transition probability matrix are close to the empirical estimates, and also the rewards are close to the empirical estimates. How close they should be? Well, depends on how many times you have visited a given state action pair. If you visit a state action pair very frequently, then they should be closer. Otherwise, they have to be farther away. So the construction of this is that you take all PR such that P hat of the next state distribution given SA minus P SA in one norm is smaller than or equal to C times square root log, and here we have the usual things. Somehow this depends on the time, so you will have a T, and maybe you will have some other constants. I don't want to write every detail, but the thing is that the important thing is that here you have to divide by the number of times you have visited a state action pair. And since it might happen that you're not visiting state action pairs, you haven't visited a state action pair at any time, then maybe you should take the maximum is 1. So you take NSA max 1. And the same way for the rewards. So the difference between a potential reward, RSA, and your estimate, R hat SA, should be less than or equal to, this is C1, this is C2, these are just numerical constants, log TC divided by NSA max 1. So you collect all this, and then you let it go. This is the algorithm. Does this work?
I didn't, maybe I missed something fundamental. Why are we maintaining confidence sets and not just the empirical estimates?
So why do we care about the
Even in
confidence estimates?
Yeah, even in the linear bandits case and here.
Right.
Why
So,
wouldn't we just maintain p hat, r hat?
right. If you go back to the finite arm bandit case, if you estimate the mean rewards for the arms, okay, let's say you have 2 arms. The first arm is the optimal arm, and it's a barely 1/2 payoff. Okay, so with probability 1/2, you get a 1. With probability 1/2, you get a 0 if you pull that arm. The other arm, that's a suboptimal arm. It has a payoff of 0.5 minus epsilon deterministically. When you pull that arm, you always get that. It's a little bit worse on average than the other arm. So if you start to play in this bandit, then with very high probability, it happens that the empirical mean for the first arm is going to be lower than the empirical mean for the second arm. If you just go with the empirical means and play the best according to your estimates, you're never ever going to choose the first time again. Never ever. So that means that you're not going to update its empirical estimates, and so you get stuck with the suboptimal arm. So you want to somehow facilitate exploration, and one way of doing this, a good way of doing it, is by using optimism. Another way would be epsilon greedy, that probably more people know about. The problem with epsilon greedy is that if you, no matter what problem you have, there is a good schedule with which you decay epsilon to 0, but knowing such a schedule for all problems, such that in the worst case, like ahead of time, like you have to decide about the schedule with looking at the problem. It's not, you can't really cheat of trying different schedules and choosing the best one. You can't really do that. It's really hard to do that. So that's why people turn to this optimistic principle. It's like a nice general way of ensuring exploration.
Excuse, so
Yes.
what about that objective function here in this MDP setting? We had that.
Right, so we have to modify that, right? So that doesn't look good. Like this inner product, it doesn't make any sense.
Yeah. So the analysis you might have done for even Hilbert space and things like that, but in this setting we should know what is the space we are working.
Thanks. This is bad, right? So first I should modify this to pi, and then what the heck is this inner product? Well, the inner product is not defined, right? So I could define it, but then it wouldn't be inner product. So what you need there is really, what is the value of that policy? What is the value of the policy in that MDP? So theta represents an MDP, a pair of P and R. And so you're asking, what is the value of the policy in that MDP. So this is going to be defined as the average value, average reward, long-term average reward of pi in MDP theta. That's a good point. The inner product was totally not defined. So this way you can actually execute the algorithm, right? So Ct minus 1 is defined. Well, the question is whether you can solve this, whether you can compute this efficiently. It turns out you can. So I talked about before that this optimistic computation is not always possible to do efficiently. Like sometimes you can prove that it's NP hard to do. So, but not in this case. In this case, you can compute it efficiently.
So here we have multiple MDPs actually, right?
Right.
For each theta you get an MDP.
Right. So this looks like a very scary computation, but apparently if you write it out, you can write some form of extended value iteration for this, and it works. You can somehow treat the unknown transition probabilities as actions, as you would choose, and you can write a form of value iteration that you can show is going to converge to the optimal value in this kind of like bigger MDP. So you can think that at every state you have a choice of choosing the next state distribution up to this constraint here. And you can write this out and you can write down the algorithm. It's efficient. You can prove it. It's polynomial time. It's fine. Okay. Yeah, the question is whether this is going to work. So that's our candidate. It's just we are applying this optimism principle to MDPs. We just like literally transfer the principle to MDPs. Okay. So what do you think? Is this going to work?
Different question. So in the linear bandit case, the confidence part was intuitive because you have the reward which is linear, and this confidence what you add is like a variance of standard deviation term. You're saying that the reward can be at most. So, and then you got the theta star to show, you showed that theta star was sitting in the ellipsoid. But I don't get the parallel here. You're just saying here in the MDP setting, I can't see the parallel here. I'm not clear on.
So what is that you're missing?
So there you, in the linear bandit case, you showed that the true parameter theta star was sitting
Right.
in the ellipsoid.
Right.
But
Okay.
yeah.
So here, okay. So how do I justify that this is a good confidence
Yeah,
set?
this is a
Okay. So this is your empirical estimate,
right.
and that's just some p. But we know that the empirical estimate is going to be so close to the true value, right? So Hovding's inequality can be used to quantify like how close you're going to be the true value. So empirical means are close to the statistical mean, and there are the state inequalities that, like Hovding's inequality would be one of those inequalities that quantify this, like how close the empirical mean is to the true mean, and just use that. Okay. So use that for both R hat and P. Just this basic principle. You think about central limit theorem, whatever, right? So the empirical mean is going to be close to the true mean. I just need some way of quantifying this. And there are this beautiful, rich literature about these inequalities, these state inequalities that actually just do that. I'm just relying on those here. I'm just the user of those inequalities.
Yeah, for that, what is not clear is you have to ensure that all state actions are like sampled well enough. And, right?
So some of these intervals are going to be really big. So if you haven't visited a state action pair a whole lot of time, then this interval is going to be big. So they are non-uniform. They're not of the same size. And you also have to make sure that these hold simultaneously for all state action pairs. So you are going to introduce some union bonds to make sure that like that inflates the logarithmic factor a little bit. But it just means it increases the logarithmic factors if you vary both like that. So that's a mild increase. Okay. Yes. Oh.
With regard to your question whether it's going to work, as you said, this is without looking at the problems, so probably it will work worse than tailoring an epsilon grid exploration.
Right.
I mean, your question was whether this is going to work.
Yeah.
Right. So I'm just saying that if you can tailor a changing epsilon greedy exploration strategy, that will work better than this.
But that's almost like saying that if I knew the MDP, then I could design an algorithm that works better. So isn't it like where is the limit of like this tailoring and cheating, right? So you really have to commit to something before you see anything, right? So that's the fair game. It's not a fair game to say that oh, I'm just going to tailor things. It's not. I mean, even if you want to, just like referring back to what Sridhar said, like you want to have these robust algorithms that work, like you can put them on the Mars. It will be too late to start to experiment with the Mars Explorer when it's already deployed. You can't do that. So epsilon grid is seems like a great idea, but eventually it's maybe not so great. I mean, it gives you some exploration, so at least you don't get stuck. But whether it's great or not, it's largely problem dependent, and this is what we don't like about it. We don't want an algorithm whose success totally depends on which problem you're trying it on. Yes?
My question is, in the previous case, we had a clear understanding of the regret. So in this particular MDP setting, I am not very clear how that regret is defined.
Okay.
Because the pi star will correspond to the optimal policy or something. What are we trying to find out?
Right.
So
yeah, but you just said it.
no,
so the regret, yes, it's a valid question. So you have to redefine everything, right? Because in MDP setting. So what would be the concept of the regret? What would be your idea of the regret? How would you define regret if it was up to you?
So since we are having multiple MDPs,
no. You only have one MDP that you run your algorithm in. So when you define the regret, you have to measure the performance relative to the true world. Like theta star, it was unique. Right? In the linear bandit case, theta star was given, it was fixed. That's our MDP. So we chose the best action there. So what's that here?
It's the best policy.
It's the best policy.
In that particular MDP?
In that particular MDP that we don't know. And we look at how much reward that collects, and we compare ourselves to how much reward we collected compared to that reward that we could have collected if we used the optimal policy from the beginning of time. And the regret is going to be the difference of the two. Okay? Yes?
So I'm not clear with your algorithm yet, right? You have these confidence bounds at any point of time on the transition probabilities and rewards. And so what is your action going to be?
Okay, maybe I didn't say that. Maybe I said it too quickly. So you choose a policy every time step, and you're at a state. You already have a policy, you just choose the action according to the policy.
No, but what is your policy?
Your policy is pi t. It is selected by this rule, by the optimistic choice. So here rho is the average reward.
Okay.
Under policy pi in MDP theta.
So theta is chosen optimistically based on your confidence estimates, and then pi is the optimal policy in that MDP you sample.
That's right. So you can imagine this two-step process that you select the best possible word, and then given the best possible word, you find the optimal policy there, and then you follow the optimal policy. Yes.
So this p hat and r hat is it's constructed from the samples from the policy pi t, right?
Whatever we follow, yes. Whatever data we see.
I mean, but finally, if you are only interested about the average cost, might as well follow the policy and compute one number. Why do we even have to compute? I mean, things are happening through. I still don't get the connection between
So you don't get the connection between what?
So how will you ensure that you are sampling each and every state action like infinitely often? Because
Well, maybe not. It's maybe implicitly assumed. Like the way in a bandit case, finite and bandit, if you're optimistic, like did we ever like explicitly force the algorithm to try all the actions? No, it just happens. Why does it happen? Because if you don't try an action, then its confidence widths are going to grow actually. There's this logarithmic grow here, right? So it becomes increasingly more precious to you. And eventually, even if the others are kind of like just staying around, this is going to overtake and you're going to take that. So the same way here, in an implicit, rather implicit fashion, it happens that you look at the best possible, you try to find the best possible MDP. So what's that? If you haven't gone to some part of the state space, you will think that that's heaven. There's a lot of reward that you could collect there and you could just stay there forever and then like be happy, right? So you go and explore. So these algorithms really systematically try to explore, always assuming the best. But when they see that, oh, that's not really working, they're not going to be stupid. They give up, right? They will try other things. And eventually they find what's the best. And it's important actually that you do have to do this systematic exploration actually. If you, like a lot of people worry about like, oh, I have to play safe, like it's dangerous to explore the state space. It's like, if I go there, I might die. Well, bad luck, right? Because I mean, if you're not exploring, then you will never ever get to see the good things, right? So of course it would be a totally different problem if we would be very serious about this dying, right? So you have your agent, maybe it's a robot, it's a multi-million-dollar robot, and you don't want it to break too often at least, right? If it costs too much to fix it, then what you can do is that you can try to build in prior knowledge that, okay, I already know that this part of the state is bad, I shouldn't go there. You put in the brakes. But the principle should be the same. It just, you are right now imposing your human knowledge on the top of the algorithm. You can still be optimistic within reason. It's not optimism without reason. It's not optimism just like that. It's optimism within reason. That's what you have to apply.
So let us say we run the normal Q-learning.
Yes.
And then with the exploration with the kind of UCB kind of upper bounds, based on number of samples you require, number of times.
For the action values?
Yeah, instead of using the epsilon greedy exploration, let's say in Q-learning, we use the kind of exploration that UCB gives, like number of times that state is picked divided by the number of state action pair it has selected. So
but you add that to what? Like the action values, the Q values?
To the Q values.
Okay.
So and I do that. Basically, I'm trying to explore in a very aggressive way. Basically.
Right. So the problem is that looks at the short-term uncertainty. That looks at the uncertainty at the state action pairs only. It doesn't look into that, if I take this action, I might actually get that far away.
So that is
right?
Captured by the Q values, right?
Well, maybe not, because they are uncertain. So the long-term uncertainty of the Q values is not faithfully taken into account if you just look at how many times you visited a state action pair. Because the underlying uncertainty also depends on where can you get from that state and how much uncertainty is left in that part of the state space. And that's not captured. You have to propagate that. And this is actually doing it. Okay. Good. Very good. Like these questions. Okay, so yes, one more.
Really more a comment than a question, right? So this principle of optimism in the face of uncertainty is something also you see with just optimistic initialization of values,
right,
which is really key to like Rmax giving a pack bound.
Right.
So it's not a regret bound but a pack bound.
Right.
But you seem to be doing the same thing in the space of transition
Right.
probabilities and you're getting a regret bound.
Yes.
Do you have an understanding of why these two are different? Whether you could do something like this with values instead of
So,
probabilities and rewards.
so there are multiple questions here. So can I use optimism to get peg bonds, and can I use high initialization to get regret bonds? That are the two questions, right? So yes, you can use optimism to get peg bonds. It's not hard. And the other question is whether high initialization is going to give you regret bonds. No, it's not enough. It decays too fast. The high initialization is going to, like, because you take averages, it decays at the rate of 1 over t. And you're looking into 1 over root t decays here. So the confidence, like somehow the upper bounds decay at the rate of 1 over root t to the true mean. And if you initialize high, that decays 1 over t at the rate of 1 over t. You might be lucky when you're experimenting with it, and it might work sometimes, but it's not a good algorithm. Alone, it's not sufficient.
Would probably be controlled using your learning rate, no?
You could use a larger learning rate, like 1 over root t.
Yeah.
Right, and then you are back to the worst case kind of like framework when I mentioned that the learning rates are typically larger. That could be interesting. I don't know whether, like how it actually plays off if you do that. That's interesting. Good. Any other questions? So, is this going to work? Back to the question. So now we discussed really how to do this, how this works. Well, bad news, no. This alone doesn't work. It actually sucks big time. Why? The problem can be illustrated on a very simple MDP. You have two states, okay? And you have two actions. Finally, I'm going to use colors. Okay. So that is state 1, and this is state 2. And the word is deterministic, okay? So you have two actions. You have a stay action, and with probability 1, if you choose stay action in both states, you stay. Okay? And your payoff, good news, is going to be 1/2. Why 1/2? Because I like the rewards between 0 and 1 and so on. Okay. So that's your reward. And you have another action to move. And the reward for that is 0. Okay? That's the MDP. And imagine that you start in state 1. And I already told you the transition properties. So we modify this algorithm that there is no uncertainty about the transition properties. All the uncertainty is about the rewards. So initially you don't know the rewards. Okay? And okay, so maybe I'm going to be even like more restrictive. I'm going to tell you that this gives you 0 reward. No uncertainty about that. But we don't know how much reward we are going to get in state 1 and state 2. Okay. So what does the algorithm do? Like initially it's going to assume that, well, the maximum possible reward is 1 in both states. Okay? So initially it thinks that this state has a reward of 1, this state has a reward of 1. What is an optimal policy? Stay where you are, right? Whenever you move, you're losing. Don't do that. Stay. If you stay, fine. So initially the reward for this guy was 1, the upper bound for the reward was 1. If you stay, you're going to see the 1/2. So you're going to adjust. It's not stupid, right? So it's just going to lower the value, the upper bound for the reward for the state. So let's say we lowered it to 0.8. So we have an upper bound of 0.8 here, upper bound of 1 there. Like that's the best possible world. In this best possible world, what is the optimal policy? We are still in state 1, and we are going to choose move. From this state we should move, because the upper bound there is larger. So we're going to move. Move, you get the reward of 0. Okay, you might see the story by now. So now we are in this state, it looks great, there's an upper bound of 1. The optimal policy says stay. You stay. You see a 1/2. You lower your estimate, it's 0.8. Okay, now everything is equal, you stay, but then you lower it again. Oh no, it's 0.7. Then you move again. So you're going to repeatedly going back and forth between the two states, continuously losing reward. You're always curious, oh, the other state is better. Oh, this is better. Not good. Switching policies too often by being optimistic is not going to pay off. You have to stop it. So you have to be patient. So the modification to the algorithm that is required to make it work is that you're going to stay with the same policy for a while. So you can't switch policies that often. So what you're going to do is that you have a counter, like how many times you see a state action pair. And if you ever see any of the counters doubled since the last time you changed the policy, then you say, oh, I learned enough, but not before that. So if you do this is called rare switching or lazy switching, then you fix this problem. Because now you're going to wait increasingly more time before you switch. It's kind of like a logarithmic time scale that you're introducing, or exponential, the larger increasing spans of time. And why is it justified? It's justified because the uncertainty is not reduced significantly before you double your number of samples. So if you look at here, if you double your number of samples, then you are just reducing a little bit the uncertainty. So just seeing one more sample is not going to change anything if you have already seen many samples. Okay? So you have to do this modification, or the algorithm is going to be always very curious about the other part of the word, and it's along the way might lose too much reward. So that's the modification that you need. And then the algorithm that you get is called UCRL2. It had a previous version. That was also okay, but this is better. And it goes by Peter Auer and a guy called Yaksh. And I think Ronald Order is also on the list of authors. And they show all kind of nice properties for the regret of this algorithm, that like it's essentially unimprovable for large class of NDPs. Okay, it's a simple idea, but you can make it work. So this is fine, finite MDPs. Can we do better than this? I mean, yeah.
So how is this what's the difference between this case and let us say I put just a multi-arm bandit with 2 arms with these 2 situations, except for that there is no transition?
Because you pay for every transition, that's the difference, right? So you pay a cost, like it's implicit because your reward is 0 when you're moving.
But then in the multi-arm bandit case,
there is no such thing. Switching doesn't cost you anything.
Correct.
Sometimes this is called just a switching bandit.
Correct. So switching doesn't cost you anything, but even let us say it cars, the switch between any two arms is like much lesser, right? So you only visit the non-optimal arms very much less frequent than the actual optimal arm, right? So
Realize that in this case, both arms are optimal. So you want to visit them equally often. So UCB would choose them equally often. So it's a very evil example. Yes. Okay, so this is great. Finite MDPs, we can do finite MDPs. This is not actually the algorithm that I showed you the first day though. This is a little bit more complicated to code up because of this step, this joint optimization. And I still have to do that. But the algorithm that I showed you is also has a very, very long history. It goes back to Thomson, who was the first guy who ever thought about bandits in the 30s. And he immediately came up with an algorithm that was forgotten for a long time. And during the last couple of years, the algorithm was revived, and it's called Thomson sampling or posterior sampling. And that is the algorithm that I used. So that algorithm, it's kind of like a very interesting twist on things. It kind of mixes Bayesian ideas. I mean, it uses a Bayesian idea, but you don't have to be Bayesian to actually buy it. It also works in a frequentist context. So you can prove kind of really similar regret bounds for Thomson sampling that you can prove for these other algorithms. So what is this Thomson sampling? So I'm just going to talk about it very briefly in bandits. I'm going to explain it in bandits, and I will tell you like how you could generalize it to MDPs. So in bandits, let's say you have Bernoulli bandits. So we have to be parametric. So we assume a parametric distribution of the arms. So for each arm, we know that the payoff is either 0 or 1, so it's a Bernoulli distribution. But we don't know the parameter of the distribution. Okay? So if you're Bayesian, then you assume that everything has a prior, like all these parameters do come with a prior. So might as well do that. So you assume that you have prior. Let's say uniform prior at the beginning. It's like a beta prior with some parameters. Okay? And if you pull the arms, you make observations of the arms, then you can update the prior, make it into a posterior. It's going to be another distribution of the parameter, of the unknown parameter. That's what Bayesian people do, right? So they keep distributions of unknown parameters. So you imagine that you pull the arms a few times, and you have all these distributions for the different arms. So how to make a decision, which arm to pull next? Thomson said it's really simple. You just draw from this posterior distribution for each arm a parameter. Okay? So you have a posterior distribution for the first arm. It's a distribution between 0 and 1, like it's maybe peaked around the mean, the empirical mean, right? But it has a distribution. So you draw one sample from that. You do that for the next time, and the next time, and the next time. And then you just choose the arm which has the highest sampled mean. So these represent the mean values, possible mean values for the arms. And you just choose the arm which has the highest value that you drew from these posteriors. Okay? So because you are kind of randomly, like you're drawing at random from these posterior distributions, you can feel that this algorithm is going to explode. It has a chance of trying things which are currently do not look the best. Okay? This is the whole algorithm. It's very simple. And you can generalize it. You can make it very, very general. You can say that, well, I have some complicated model, like an MDP. Okay? And I don't know what the true word is, but I keep a posterior distribution over the true word. Because in the bandit setting, it's like the arm distributions, they are the word, right? So the actual parameters, that's the word. And this posterior distributions that you're putting on the arms, the product together determines a joint distribution over the word, over the possible bandits. You're just drawing one sample when you are independently drawing parameters for each of the arms, then you're just drawing from this joint distribution. So you can go back to your MDP setting, and you can say that, well, I need the distribution over the possible words, and I can generalize Thomson sampling to this setting. So this is exactly what you can do. So for the finite MDP setting, since you have this category of distributions for the next states, people like to use conjugate priors so that it's easy to keep around the posterior distributions, easy to sample from those. And if you open up a Bayesian machine learning textbook, then you will find that, well, an appropriate distribution family is the Dirichlet family. So they are going to choose a Dirichlet family, and they are updating the Dirichlet parameters. It's the same thing pretty much as keeping empirical estimates, just that you will have full distribution. So you can sample for each state from the Dirichlet distribution that you updated, an X state distribution. And for the rewards, maybe you just do this Gaussians, with Gaussians, right? So you have a conjugate prior, and all posteriors are going to look Gaussians. So you sample the rewards as well. So now you sampled an MTP. For each state action pair, you sampled transition probabilities, and then for each state action pair, you sample the reward. That's a possible word. You find the optimal policy in that possible word, and you follow it. Because of this example, you might suspect that that's not going to fly. That's not going to work really well. So you kind of have to slow down things a little bit. And then there are, again, like you can introduce the same thing in a finite MDP setting. You could say that I'm not going to change policy until I see that at least one of the counts for my state action pairs has doubled since the last time I chose a policy. If you do that, that's the algorithm that I coded up. It works pretty well. And you can even show that it works well. So more recently, we've been working on generalizing this to much larger classes of MDPs. So in the previous work, we generalized this optimistic setting to linear quadratic regulation. So that's like a nice classic set of problems. And there we became really interested in going even beyond, even richer class of non-linear control problems. And with this Thomson sampling, the good thing about this is that this joint optimization could become really hairy if you have a more complicated model. Even for the linear quadratic regulation, like we don't know how to solve this efficiently. With Thomson sampling, it's very simple. You keep your posteriors, you're sampling from your posterior, you just have to solve one optimal control problem. It's a model-based control problem. So nothing can be much simpler than that. And so you kind of get this exploration for almost for free if you do these things with Thomson sampling. Okay, so in summary, so we came a long way. I should actually put up the URLs on the board so that you can download my code. I will do that after I finish. And then you can copy just the URL. It's a pastebin URL, so you will get the code from that, and you can experiment with that. So we started with these codes, and we saw that if we just do the exploration in a simple fashion, epsilon greedy is not going to cut it for even very simple MDPs like the reverse swim example. So you need a more sophisticated set of tools to deal with exploration. Actually, in Sridhar's talk, when he was talking about like why DeepMind's algorithm might fail for some of the games, my thinking is that for some of those games, the problem is that it's really hard to get by the rewards. It's like the reverse swim problem. You have to like make a conscious effort to go to some place and get that. And by just randomly trying, using epsilon greedy, it might not work. It very much depends on the game that you're talking about. For many of the games that are way up on the list, it's really easy to get rewards. For the other games that are in the bottom, I think that it's not easy to get the rewards. And so clever exploration is really important. We have a number of tools that we are playing with. Optimism is one of them. I didn't talk about, but you can use confidence sets differently. You can play these elimination-based algorithms, and then sometimes they are a good alternative to, that's kind of like, just play the arms as long as uniformly often, as long as you can't prove that they are suboptimal. And that's a good alternative to optimism. And Thomson sampling is the new content there, which is very promising. It's somehow harder to theoretically deal with Thomson sampling. There's somehow too much randomness in it. But we are kind of getting there. And Thomson sampling maybe has the best chance of giving you computationally efficient solutions to a large class of problems. But we are, I would say, at the very beginning, and this is going to be a long road until we have algorithms that are able to deal with reasonably sized real-world problems in a useful fashion. Okay, thank you. Right.
Could you write down the regret bound, the upper bound on like UCRL or Thomson sampling regret?
So Thomson sampling for linear bandits, for example, that's easiest to answer, is going to give you a slightly worse upper bound. It's d to the 3 half time root n.
Right, but I'm
So
asking
it's
about the MDP.
suboptimal.
Sure. I'm asking about the MDP.
For the MDPs, I don't know it off the top of my head. Is the paper by Daniel Russo and
Sure,
Benjamin
I can look
Monroy.
it up. Okay.
For UCRL, it's basically the diameter of the MDP is going to play a role. So there are some conditions on the MDP. It should be a communicating MDP. If there are states that you can never get to, like transient states in the MDP, then UCRL is not the algorithm to use. In fact, you can argue that with transient states, it's not easy to deal with them in this setting. But if you have an MDP that is communicating, that means that from any state you can reach any other state. Then the diameter is this concept of how fast you can do that. Like you take the best possible policy that brings you from one state to another state. Then you can show that the regret should grow if you have larger diameters. And UCRL is getting the optimal rate in terms of the diameter. And I think it's, I'm not totally sure about whether it gets the optimal rates in terms of everything. It's definitely a root n rate, and then the size of the state space action space is going to appear in addition to the diameter.
Okay.
Yeah.
So I think,
Coming back to the previous, this example, so if you evaluate the average cost, you are going to move once, right? But you still stay, the optimal policy if you implement, it's going to say move once, but stay put at state 2. Or move once, stay put at state 1, right? In which case the average will turn out to be still half. Initially you are going to go to 0, but if you are saying that the evaluation is argmax or the average cost of the policy, if that is what we are saying, then it will still be half, even if you are going to move once and then stay put there, because you are going to implement that policy, right?
No. Okay, so I think that what you're missing is that you don't know that the average reward is half. You only deal with the upper bounds.
That's true.
And so the upper bounds were changing. So if you have an upper bound that's higher, like an upper bound on the reward, you are going to take that as the reward at the state, if you stay. And if you have a higher reward at one of the states, then the optimal policy wants to go to that state because that cost of just going there is going to be negligible compared to the reward that you're getting afterwards.
No. So, but when you say the evaluation is average cost,
Right.
then it means you are going to go to that state. But if the policy is optimal with respect to whichever MDP you are evaluating, it's going to say move to that state and stay put in that state.
Right.
And either you are calculating the actual reward of half, or you are the confidence or upper confidence bound that you are calculating. If you are evaluating the average policy, then the average cost, then it is going to be a non-negative number. It's not going to be zero. I'm only talking about if you're.
So the optimal policy is
So
in the true MDP, the optimal reward, optimal average reward is going to be 1/2, right?
No. Okay. Let me rephrase the question. So when you are saying regret, are you going to measure it with respect to the reward that you pick every time instant, or through that definition?
So so I never wrote the regret definition, but this is the time to clarify it. So the regret is going to be how much reward I could have collected from the beginning of time if I use the optimal policy in the true MDP. So that's n times, and the maximum over all policies of the average reward in the true MDP. This is how much reward I could have collected, right? So this is going to be 1/2 in this example, n times 1/2, minus the reward that I collected, right? So I care about the actual reward that I collect. I want to maximize the reward. So this answers the question, I guess. Okay, good.
Okay, this is Shama's final thought, but you're going to get till 5.
I'm going to be around, yes, and please